body systems to exercise. Respiratory responses. This is a graph to show the change in volumes when ventilation increases. When the ventilation increases, so does the tidal volume, which is the volume of air in each breath. The medulla respiratory center, found in the medulla oblongata, sends signals to the respiratory muscles to contract harder and faster so that the rate of respiration increases. Inspiration and expiration occurs more frequently. During exercise, muscles are in need of more oxygen and need to expel waste products such as carbon dioxide. Therefore, the increased rate of respiration means that oxygen can be supplied to the muscles and carbon dioxide can be diffused into the alveoli and be exhaled. Respiratory dynamics. Ventilation equals breathing rate times tidal volume. In the equation, the VE stands for ventilation, BR stands for breathing rate, TV for tidal volume. Ventilation is the total volume of air entering the lungs in a minute. Tidal volume is the amount of air breathed in with each normal breath, and breathing rate is the number of breaths in a minute. Therefore, the equation tells us that it's the total number of breaths in a minute, as well as the volume of each breath, to give us ventilation. At rest, the normative values for ventilation is 6 litres per minute. The breathing rate is around 12 breaths per minute. The tidal volume is about half a litre. However, these values change during pre-exercise phase, and this is known as the anticipatory rise. This is just before you exercise, when your heart rate and breathing rate increase because the brain knows you're about to exercise, so prepares the body by the release of the hormone adrenaline. An example of this is as a substitute in football, about to come onto the pitch, your heart rate and breathing rate will increase from adrenaline. The breathing rate may increase to around 20 breaths and tidal volume around 600 millilitres, and ventilation to about 12 litres. At moderate exercise, these values will change. Breathing rate will be 30 breaths, tidal volume will be 1,500 millilitres, and ventilation will be 45 litres. At maximal exercise, the values will change again. 40 to 60 breaths for breathing rate, 3,000 to 4,000 millilitres for tidal volume, and ventilation to 120 litres. However, these values are averages and are dependent on age, medical condition, current fitness level. For example, athletes would have a ventilation of around 7.5 litres at rest, and at maximal exercise around 180 to 200 litres. The reason for this being that athletes train much more than regular people, and therefore their respiratory muscles have adapted to the demands of exercise and become stronger so that they can contract harder with each breath, forcing more air in and out, meaning that more oxygen can be supplied to muscles. When exercising, the way in which air enters the lungs is at a much faster rate. This is explained to MVPA: movement, volume, pressure, and air. Firstly, in inspiration, the external intercostal muscles contract by accessory muscles such as the scalene muscles and the sternomastoid, helps to raise the ribs up and sternum. The serratus anterior to elevate the ribs, and the latissimus dorsi to lift the lower ribs. The pectoralis major contracts, causing ribs to move outwards to decrease the pressure as much as possible and as quickly as possible. The diaphragm during active inspiration flattens as usual. This causes the pressure inside the lungs to dramatically decrease, and therefore from Bohr's law the volume also rapidly increases. This causes a steep gradient of pressure in the external environment and internal environment, and air always moves from high to low, so air is sucked in very quickly. However, when active expiration occurs, the external intercostal muscles relax with the aid of accessory muscles like the anterolateral abdominal wall and the innermost intercostal and internal intercostal muscles. All of these accessory muscles help to decrease the pressure inside the lungs by forcing the ribs in and down, and the anterolateral abdominal wall increases abdominal pressure, leading to the diaphragm being pushed upwards into the thoracic cavity. Therefore, the diaphragm will become dome-shaped, and the overall pressure will increase, and thus the volume will decrease, so air will move from internal environment to external environment rapidly. The ventilation of breathing therefore also increases, as more air is being sucked in and out during expiration and inspiration during exercise. Receptors and triggers controlling forced inspiration and expiration. There are always receptors monitoring levels of oxygen, carbon dioxide, temperature, pH, and movement. There is peripheral feedback and central feedback. Chemoreceptors monitor levels of CO2, pH, and oxygen in the blood. Proprioceptors detect movement, and thermoreceptors monitor the temperature. This feedback is sent to the medulla oblongata and pons of the brain, which are also affected by emotional stimuli from the limbic centers and volitional control from higher cerebral cortex. Based on the feedback, an impulse is sent along the intercostal nerve or phrenic nerve to contract respiratory muscles. So, during active inspiration, the dorsal respiratory group and inspiratory center of the ventral respiratory group becomes active, and the expiratory center of the ventral respiratory group is inhibited, which causes the diaphragm and intercostal muscles to contract and the expiration muscles to relax, leading to inhalation taking place. So during active expiration, the dorsal respiratory center and the inspiratory center of the ventral respiratory group are inhibited, meaning the expiratory center of the ventral respiratory group is active. Therefore, the muscles of the expiration contract and the muscles of inspiration relax, so expiration occurs. The ventilation increases from at rest to exercise greatly, and this is also because more frequent impulses are sent to trigger inspiration and expiration when exercising, as muscles need more oxygen to carry on working. The Herring-Brewer reflex, named by Joseph Brewer and Ewald Herring, is a reflex involving a prevention of overinflation of the lung. This is because stretch receptors, which are located in smooth walls and pleura of the bronchi and bronchioles, respond to air in lungs. Information is sent to the medulla oblongata via the vagus nerve in order to stop inspiration. Then, whilst expiration first occurs, the stretch receptors are not stretched anymore, and impulses are no longer sent, and the process can occur again. It is a protective reflex to prevent overinflation from inspiration of the lungs. They are usually only used during active inspiration during exercise, while the inspiratory muscles are working to increase ventilation. Expiratory control center. The medulla oblongata is the main respiratory control center, and it functions to send signals to muscles, telling them to contract, causing inspiration. There are two groups in the medulla that control breathing: the ventral respiratory group and the dorsal respiratory group. The ventral respiratory group stimulates expiratory movements, whereas the dorsal respiratory group stimulates inspiratory movements. When exercising, the proprioceptors detect more movement occurring, and thermoreceptors pick up an increase in temperature, so impulses that are sent from respiratory control centers become more frequent, telling respiratory muscles during inspiration to contract faster and harder with accessory muscles, and also at expiration via the ventral respiratory group, telling the expiratory muscles to contract, and accessory muscles to also contract, which will lead to an increase in ventilation as more air is being taken in and out of the lungs. The Valsalva maneuver is a practice breathing technique which causes trapped air and pressure in the thoracic cavity and the abdominals. The maneuver is exhaling forcefully against a closed airway. You inhale and brace down, keeping the core tight, and then release and exhale air in small quantities against a closed airway. The closed airway is the glottis. For example, in test application during a deadlift, instead of breathing in on the way down and exhaling on the way up, you should inhale all the way in and hold this whilst you execute the deadlift, and keep the core tight whilst it is full of air, and as soon as you come to the end of the lift, you can slowly release air sharply. This will help to prevent injuries occurring, as the whole body is supported by the pressure of the air. In everyday life, the breathing technique can be used when popping ears like on an aeroplane, or when scuba diving when the pressure changes and an equalization needs to occur to balance the pressure. In sporting examples, the Valsalva maneuver can be used such as in weightlifting, shown in the top right corner, when attempting to move a heavy object that will use a great amount of force or power. Squats, deadlifts, and bench pressing are common exercises that use the Valsalva maneuver. It is advantageous to use the maneuver because it stabilizes the trunk and is a good force generator. Therefore, when trying to move a heavy load, you need a stable trunk, otherwise an injury could occur, and you would need a large amount of force to be made, and the breathing technique helps with this. Another application is in rugby when a tackle is going to be made. Just before the two players collide with each other and impact is made, the Valsalva maneuver can take place, and the force of the tackle can be absorbed much better, whereas if you didn't do the maneuver, there could be serious damage. In the graphs, it is showing the breathing rate during a Wingate test and during a multi-stage fitness test. A Wingate test is a fitness test usually testing for power in the legs of a performer. To perform the fitness test, you need a psycho-ergometer. You will need to be able to record the time with a stopwatch and weigh the performer. Firstly, calculate the body mass of the performer and calculate the test weight, which is 7.5% of the body mass. This test weight is added to the psycho-ergometer, and after a warm-up, the performer should Begin cycling at a speed of around 60 RPM on the cyclometer for 10 seconds. Then, after this, a countdown, and the performer should pedal as fast as possible for 30 seconds with the test weight. The power is then recorded on the computer software. In this analysis, the Wingate test is only used for 15 seconds. The multi-stage fitness test is the other fitness test used in the investigation analysis. To perform this test, you will need to place cones 20 meters apart and play the recording of the bleep test on audio. The performer should then run, jog or sprint between the 20-meter cones inside the set time for the bleeps. The stages get harder as you progress into the test until eventually you cannot carry on anymore. It is a maximal test which pushes the performer to the limit. In figure 1 it shows that at rest the breathing rate is 13 breaths per minute. The estimated tidal volume at rest is half a litre. Therefore the ventilation is around 6 litres. The performer's body is supplied with enough oxygen with this number of breaths, and the level of carbon dioxide can be expelled. At this point there is no forced inspiration and no accessory muscles are contracting. Pre-test, the breathing rate increases to 14 breaths per minute. This can be due to the anticipatory heart rate rise, whereby the heart rate rises, circulating more blood around the body, ready to supply muscles with oxygen and expel waste products like CO2. This means that the breathing rate must also increase to inhale more oxygen and expel more carbon dioxide. This process occurs due to the release of adrenaline and noradrenaline from the adrenal glands. However, once the Wingate power test starts, the breathing rate will increase too, to cope with the demands of the high-intensity exercise. 36 breaths post-test. The estimated tidal volume at maximal work is 3,000 to 4,000 millilitres, and the ventilation is 126 litres. The sudden increase in breathing rate is due to receptors such as proprioceptors detecting the level of movement. At rest there was not much movement, however once the test began, the proprioceptors detect a large amount of movement and sends this feedback to the respiratory control centre, whereby signals are sent back to the respiratory muscles telling them to increase breathing rate. Chemoreceptors also detect a change in the level of oxygen and carbon dioxide in the blood, and also levels of blood lactate. The Wingate test requires a lot of power and works the performer maximally at very high intensity. The anaerobic stores such as the PC store and the anaerobic glycolytic store would have been recruited, which leads to lactic acid being produced as a waste product. The chemoreceptors would detect these varying levels, as well as the drop in the level of oxygen in the blood, as working muscles have used it up and the level of carbon dioxide is increasing in the blood. Therefore, the chemoreceptors detect these changes and send this feedback to the medulla oblongata and the respiratory control center, which will then send more signals along the intercostal nerve and the phrenic nerve to increase contraction force and rate of respiratory muscles. Lastly, receptors such as thermoreceptors may have also detected the increase in body temperature, as when muscular contractions take place, heat is produced as a byproduct. The receptors will detect this change and send the feedback to control center once again. This is the reason why the breathing rate increases post-exercise on the Wingate test. The breathing rate increases as well as the tidal volume, so the overall ventilation post-exercise increases massively from at rest to supply the muscles with oxygen and expel CO2. Here's the change in breathing rate in the multi-stage fitness test at different times. At rest, the breathing rate was 13 breaths. This is because they are not working at all really, and the minimum number of breaths is needed. The ventilation at this point is about 6 litres. However, pre-test the breathing rate increases to 19 breaths per minute. This is due to anticipatory heart rate rise, affecting breathing rate. The heart rate gradually increases as the stages progress, such as in level 4 the breathing rate is 23 breaths per minute. The increase in breathing rate is due to the aerobic system must work a bit harder due to the slight increase in the intensity of the test, and muscles are in need of more oxygen and needs to expel carbon dioxide. By increasing breathing rate it means that more oxygen is diffused into the blood by a shallow gradient through the thin-walled alveoli, and the carbon dioxide that is built up can then be diffused into the external environment. As the test progresses in stages more, breathing rate increases more. In level 8, the breathing rate is 35 breaths per minute. The receptors detect all the changes in the body and send these signals to the medulla oblongata, and an increase in force of contractility occurs, as well as the rate at which they contract. This means that with each contraction of the respiratory muscles, it will be a much more powerful contraction, and the volume of air inside the lungs will be expelled much faster, and during inspiration more air will be sucked in.